All right. So again, we're working towards evaluating and finding limits. Limits are the value that a function is approaching as the variable, normally x, but it can be any variable, is approaching some value. And as I've stated, in many cases, that value that we're approaching is a non-permissive value. So we need to do something to the function to get rid of the part that makes that number non-permissive. So we're working towards evaluating limits. And we're going to see that these limits have a couple different applications. So we'll start looking at that today. Secant is a line that cuts a graph in two or more distinct points. So if you got those 2 points on a graph of the function y equals 2x cubed plus 3, we want to determine the equation of that secant line. So there's a couple different ways we can do this, but they both involve finding the slope of the line. And we can find the slope, remember, of a line. And also remember that in math, normally the letter m represents slope by using the slope formula, y2 minus y1 over x2 minus x1. So remember, we just designate one of the points, it doesn't matter which one, as the first point. So if we let a be point 1, that means that x1 is 1 and y1 is 5. The x coordinate or component at point 1 and the y component at point 1. That would mean that b would be the second point, and those would give you the values of x2 and y2. So again, you can switch these two around, it doesn't matter. You'll get the same result in the end when you plug these numbers in and simplify to get the slope. But the way I have it set up, y2 is 19 minus y1, which is 5. Remember, slope is rise over run, so the rise is the difference in two y components. The run is the difference between two x components. This will give us 14 over 1, or 14. So that's the slope of that secant line. Now, as I said, there's a couple different ways we can do this. One of them would be using the point slope form of a line, which is y minus y1 equals m bracket x minus x1. So this is used if you have a point and the slope, which we do. We actually have 2 points, and it wouldn't matter which point we put in. Remember that most equations have an x and a y variable in them. And so in this point slope form of a line, x and y are left, x and y, because most equations have x and y in them. So now we just need to choose one of the 2 points. It doesn't matter which one. I'm going to choose the first point because the numbers are a little smaller to represent x1 and y1. I've already got it labeled up here as x1 and y1. And m is the slope. So y minus y1, which is 5, equals 14, because we figured out that's our slope, times x minus x1, which is 1. And now it's just a matter of simplifying this equation. Multiply out the brackets on the right, and then we'll add 5 to both sides. And there's the equation of that secant line. Okay, so that's a secant line. A secant line is a line that cuts a graph in 2 distinct points. Now, the other way you could have found the equation of it is just go back and use the slope-intercept form. And in this case now, we would use a point for x and y, one of the 2 points, as well as m, and then solve for b, which would be the y-intercept. We already know from the work we did finding the equation of that line that the y-intercept is -9. So if you take one of the points, and it doesn't matter which point you choose, let's use the second point in this case, 2 comma 19, meaning y is 19 when x is 2. Again, the slope is 14. So this will give us 19 equals 28 plus b. And when you subtract 28 from both sides, you again will get -9 for b. Same y-intercept that we got doing it using point slope. And then you'd write the equation y equals mx plus b, where m we know is 14 and b is negative 9. So it's the same equation. So a couple different ways you could find the equation of that secant line. So that's a secant line. What we're going to be finding, though, is a tangent line. A tangent is a line that touches the curve at only one point. If the point of tangency is known, it can be used along with secant points to determine the slopes of the secant lines. As the secant or secant point approaches the point of tangency, the slopes of the secant lines will approach the slope of the tangent line. So here's what that means. I'm just going to open up a new page here to show you what that means. So let's say we have a curve. Doesn't matter what it looks like. Let's say we have a curve. Looks something like that. And let's say we want to find the tangent line at some point on this curve. So let's say we want to find the tangent line to that point right there. A tangent line is a line that cuts the graph in only one spot. It touches the graph in only one spot. So you're going to be given that point of tangency, that point that the line touches the graph. So what we will do is we will choose different secant points. So maybe that point right there is secant point 1. And we would draw a line from S1 to the point of tangency, which we'll call T, and we'll find the slope of that line using the slope formula. Okay? And you could draw that secant line. So let's do that. And I'm going to change some colors here. So this would be that secant line, which we'll call S1, secant 1. So we could use a slope formula and we could find the slope of that secant line. And next, we would choose a point closer to S1, or closer to T, the point of tangency, I should say. Say right there. And we would draw a line between those 2 points. And again, I'll change colors here. And obviously, that's a different line. That would be secant line 2, because it would be from secant point 2 to T. And this would give us secant line 2. Now that's going to have a different slope than the first secant line. You can see that they're going at a different angle. And then we would calculate that slope. And then we would keep doing that, moving the secant point closer and closer to T, the point of tangency. Every time you do that, you're going to get a different line with a different slope. But those slopes will approach the slope of the tangent line. The closer that secant point gets to T, the point of tangency, the closer the slope of that secant line will get to the slope of the tangent line. Again, this is a concept of a limit. The slope is approaching the slope of the actual tangent line. So this is a process that we can use to guess what the slope of the tangent line is. Because we only have one point on that tangent line. You need 2 points to find the slope. We only have one. As that secant point gets closer and closer to T, the point of tangency, the slopes of those secant lines will get closer and closer to the slope of the tangent line. And so by moving S closer to T, we can guess what the slope of the tangent line would be. You're guessing. So this only works if the slope is an integer, because not all slopes are. There's lots of slopes that you've seen before where it's not an integer, it's a fraction. Okay, could be a repeating decimal for the fraction, it could be a terminating. So this would only work if the slope of the tangent is actually an integer. And so we're going to learn about other methods to find the slope of the tangent so that we take the guesswork out of it. But as a starting point, this is how we're going to do it. Okay, so in this example, the following table gives the coordinates of the point of tangency, which is A. So this point A is a point of tangency, and several secant points, B sub n, and the slopes of the secant lines, A to B sub n. So B sub 1 is the point 1.5, comma 4.5. Then B sub 2 is when x is 0.8, and then 1.1, and then 0.9, and then 1.05, and then 0.95. So you see these x values are getting closer and closer to the x value at the point of tangency, which is 1. And we went on either side of 1. The first point where x is 1.5, that's greater than 1. The next point where x is 0.8, that's below 1. And then we went 1.1 for x. So you see in each case you're getting closer and closer to the x value of 1. And then we see at the very bottom here, we've got the slopes of those secant lines. We went from 5 to 3.6 to 4.2 to 3.8 and so on. And so assuming that the tangent line has a slope that's an integer, we would guess that the slope of that tangent line is positive 4. As it says, it is apparent that as B sub n approaches A, the slopes of the tangent lines approach a value of 4. So now the equation of the tangent line can be determined using this slope and the point of tangency. So again, that would be when m, the slope is 4, and the point of tangency is the point 1, comma 2. So if we use the slope-intercept form of the line, we could also use point slope like we just did. It doesn't matter. I'm just choosing to do it this way. We know that m, the slope is 4, and the point of tangency is the point 1, comma 2. So I let x equal 1, y equal 2, m the slope be 4. So 2 will equal 4 plus b, and b will equal negative 2. So now our equation will be y equals negative 2x. Sorry, not negative 2, it should have been 4. The slope is 4. B is negative 2. So that's the equation of that tangent line. And again, at this point, it's just a guess. We're assuming that the slope of the tangent is an integer, so we guess that the slope was positive 4. So here's an example where we're not given a table. We're going to have to do it on our own. Determine the equation of the tangent line in general form. So what is general form? You might remember, well, if we go back to the last example that we did, we wrote the equation in slope-intercept form. The general form of a line is ax plus by plus c equals 0, where a, b, and c are elements of the set of integers, meaning you can't have any fractions or decimals. And also normally a is greater than 0, so it's positive. That's the general form of a line. We learned about that back in 10C. So we want to write this new equation in that form. So we can do this by setting up a table of values. So we have t, the point of tangency, which is the point 1, comma 1. And then we're going to have our different secant points. So in the previous example, we said they were b sub 1, b sub 2, b sub 3, and so on. I'm just going to use s for secant points in this case. And we want to choose values of x that get closer and closer to x equals 1, which is the x value at the point of tangency. So we might start at 2 and then go down to 1.5. So in the last example, we went on either side of the point of tangency, the x value. It doesn't really matter. In this case, I'm just going to get closer and closer to 1 from the right side, values of x that are larger than 1. So I got 1.5, maybe 1.1, maybe 1.01, and 1.001. There's really no right or wrong values that you can choose here. Assuming that the slope of the tangent line is an integer, we're going to be able to guess what it is because our slopes will approach the slope of the tangent line. So we need to plug each of these x values into the equation to find out what y is. So the equation is y equals x squared. Like these are all points on the curve. So I'm going to use this equation to generate my y values. So when x is 2, 2 squared is 4. When x is 1.5, when I square it, 1.5 squared is 2.25. And then I'm going to go 1.1 squared, 1.21. And then 1.01 squared, 1.0201. And then 1.001 squared, 1.002001. So now I can use each point to find out what the slope of that secant line is. So I'll start with line segment between t and s sub 1. So m, the slope, will be y2 minus y1, which would be 4 minus 1 over x2 minus x1, 2 minus 1. So that'll give us 3 over 1, or 3. So that's the slope of the secant line from t to s sub 1. And now we'll find the slope of the secant line from t to s sub 2. y2 minus y1 would be 2.25 minus 1 over x2 minus x1 is 1.5 minus 1. So if we use our calculator here to help us do this, so 2.25 minus 1 will be 1.25, and 1.5 minus 1 on the bottom will be 0.5, so we're going to divide by 0.5. That gives us, oh, yep, yep. Try that again. There we go, 0.5. 2.5, that's better. Okay, so then we'll find the slope of the secant line from t to s sub 3. So it'll be 1.1 minus 1. Sorry, 1.21 minus 1. (1.21 minus 1 over 1.1 minus 1). So that'll be 0.21 divided by 0.1, which is 2.1. So it looks like it's approaching a value of 2. That's what it appears to. So just to be sure, let's do one more here. Let's go from t to s sub 4. It'll be 1.0201 minus 1 over 1.01 minus 1. So 0.0201 divided by 0.01, 2.01. So I think we've done enough. It appears that these secant lines, the slopes of them, are approaching a value of 2. So we're going to guess that is what our tangent line has for a slope. So if I use y equals mx plus b, and I'm using the point 1 comma 1 with a slope of 2, so 1 will equal 2 plus b, b will equal negative 1, and our equation will be y equals 2x minus 1 in slope-intercept form. In general form, it'll be 2x minus y minus 1 equals 0. Okay? Now we can do the same thing with this next example, choosing values of x that are getting closer and closer to a value of positive 2. We can do exactly the same thing and generate what that equation is. But I'm just going to skip this. I mean, it's the same thing. They're just crunching numbers in the calculator basically too, and then guessing what the equation or the slope of the tangent line is. So I will stop there, and you can start working on these questions on page 9 and 10. So for question 7a, you can do the first 6, all of B, all of C. Question 8a, you can do the first 3, all of B, all of C. And then for 10a, you can do the first 8, as well as B and C. Okay, so you can work on those questions. I will post the solutions to Google Classroom so you can check your work. And then tomorrow we'll actually start looking at evaluating these limits. So what we just did today is another example of a limit. Okay, we're finding what the value of the secant lines is approaching to guess what the slope of the tangent line is. So it's just like a limit. The slope of the secant lines approach the slope of the tangent line. So we'll start looking tomorrow at how we can actually evaluate these limits. And we'll utilize some of the tricks that we've been learning about factoring, sometimes multiplying top and bottom by conjugates,